Okay. Thank you, everybody. I would like to thank the lasers to give me the opportunity to show you our lab results in laser-induced surface structures and as a tool to modify the superconducting properties on niobium sheets. Okay, this is the outline of the talk, and I will start with the motivation. The idea is that usually vortex pinning in type 2 superconductor is essential for practical application. Defects act as an effective pinning centers, and you need them to develop applications. Usually we are dealing or we are thinking in bulk defects as grain boundaries, stacking fault, back. Usually when you are looking to the surface superconductivity, you can see that the bulk superconductivity becomes extinguished at AC2, while surface superconductivity can be observed to higher fields in more or less until 1.7 times AC2. And here you can see the case of the dependence of the VC3 and VC2 in the case of niobium at several temperatures. Okay. This application can be used, for instance, to develop superconducting radiofrequency cavities. And niobium is one of the best options because it has very low microwave surface resistant values, but it's important to control the surface characteristics in order to develop superconducting radiofrequency cavities with high quality factors. Usually, this has been done in the industry by thermal etching, electropolishing, or chemical polishing in controlled atmospheres. But we want to check if also this can be done with laser technologies. In principle, here you can see two samples that we have been working on, in which you can see, for instance, as you can induce a lattice of defects. This is a nickel plate, usually used for substrate for AC2 superconductors. And also here you can observe how we can generate nanostructures in an aluminum surface that can be used, for instance, to generate iridescence effects. Also, this was done with a picosecond UV laser. If you use femtosecond lasers, usually you can observe this kind of nanostructures. In this case, is in the tungsten and platinum surface. That also, with this, you can modify for instance, in this case, the optical properties of the metallic surface. Okay, you obtain some surface that becomes black, and they absorb completely the radiation when you just without modifying the color, just modifying the nanostructure of the surface. So the question we want to deal with is, are laser-induced surface nanostructures an alternative to control the niobium superconducting properties? And to check this, we have done several laser treatments. In particular, we have been working with 3 different lasers. In one case, is a 300 picosecond UV laser, in which we can work in different controlled atmospheres. In particular, we have been working with nitrogen and argon. Also, we have been working with an ytterbium jack femtosecond laser. And we have a collaboration with a group in Germany that has allowed us to also to check what happened in another near-infrared femtosecond laser. In this case, you see the pulse duration is 1 order of magnitude shorter, and the wavelength is also a little shorter. In principle, in the samples I have showed you, the sample is fixed, and we make a beam scanning mode. Okay, in this case, we have to control several parameters. First, you start with a laser beam that reaches your surface. In this case, you must usually, with the lasers I'm going to show you, the energy profile has a Gaussian type. So you must first to control the energy of one pulse. This gives you the average fluence, this is the energy density, and also the radiance of the pulse width. But in the following, you follow one line, and you control the speed in which you move the laser through this line. And in this case, what you have to control first is to try to obtain a uniform energy distribution along the line. You must think that you are applying Gaussians, discrete Gaussians. So if you increase the overlapping of the Gaussian, at the end, you have a near constant value along the line, okay? So we have calculated that to reach this, the distance between the center of two consecutive pulses should be shorter than 0.9 times the radius of the beam. And with this, we can control, or we have estimate, which is the energy at the center of the beam, and also which is the average fluence you are depositing on your sample. That is a given number of times the energy of one pulse. But now, also, you want to cover all your surface in order to obtain a uniform nanostructure on your surface. And also, then you must think that when you control the line in the perpendicular direction, you also have a Gaussian energy distribution. So you have something similar, and in consequence, you must control the distance between two lines and to have something similar criteria to have a uniform distribution on all your surface. And also again, the average fluence you are depositing on your surface is a given number of times the fluence of a given pulse. Also, it's important to have in mind that in this process you have several time scales, okay? You have the interaction of a given pulse with your material, and this is associated with the pulse duration. Normally, with the lasers I have shown to you, we are working with femtosecond, or even you can go to nanoseconds. Then when you move through the line, the important point is associated with the frequency. And then when you scan the area, you must think that normally the time between two lines is associated with the spin of the laser and the distance you are scanning. And this is sometimes, usually in the range of 0.1 to 10 milliseconds. So this is important because it means that it's not only important the level of energy you are applying to the surface, but also the history of how you have reached this level of energy. So I'm going to show you which are the surface nanostructures we have obtained in niobium. When we work with the UV picosecond laser, when you work with very soft laser conditions, then you obtain like a rebel structure. You mean there is some bands on your surface that they are perpendicular to the polarization of the laser. When you go to very high level of energies, then you have what we call the micro protrusions, in which you have this kind of structures, and usually the distance between two of these points is of the order of microns. And in the middle you have some structure that move from this to this. Okay. If we look to one of these structures and then we measure which is the roughness and the periodicity, you can see that more or less we have a periodicity that is very close to the wavelength of the laser we have been using, and the depth is of the order of 18 nanometers. I will then take in mind this line because then we are going to compare with the other laser. When we work with femtosecond lasers, what we have is what we call laser-induced periodic surface structures. In this case, thank you very much. In this case, when you work with soft laser conditions, you start to create these structures that you see when you increase the energy of your treatment you have a more defined structure. Also, it is perpendicular to the polarization of the laser. And, okay, we have checked, for instance, that here is the aspect of the surface. You have seen that we work with samples that we have received. We have not made any initial surface treatment to improve the roughness and the quality of the surface. Clearly, you can see that we can see clear the defects associated with the rolling direction or with the rolling protocol that was suffered by the surface. And we have here, you see that the aspect is similar. You can compare, in this case, with the 30 femtosecond laser and with the 280 femtosecond treatments. And here we have different periodicity, but this is the only difference. And also, you can see that if we change the orientation of the sample with respect to the laser protocol, we have the same nanostructure independent of how was the rolling direction. It's important to see that the level of oxidation in these samples is very low, even if we have made the treatment in air. Okay, so the reference sample was approximately a 4% of oxygen on the surface. In air, we increased to 6.2. When we work in argon and nitrogen, even we decrease a little. Also, we have observed small amounts of nitrogen in the sample that have been processed in nitrogen. Also, if you make the AFM profile, you will see in this case that the periodicity is not exactly the wavelength of the laser. It's approximately the 70% of the wavelength of the used laser, and the depth is near 10 times higher than in the case with the UV laser. Also, you can observe that between this lips structure, you can observe another structure that with period of 50 to 80 nanometers that are called high spatial frequency lips. And when you make the cross-section of this area, what you see is that you have a very nice, it's not melt. We don't have any amorphous phase. We have a crystalline phase here. And also you can observe here a line that define which is the level of the range of the thickness that has been affected by the laser. In this case, it's of the order of 200, 250 nanometers. Also, when you see the composition, you can see a small area that, or the small thickness that where you can find the oxides. In the case of the sample that has been processed in nitrogen or in argon, the thickness of the area that is oxidized of the order of 5 nanometers. It can increase until approximately 30 nanometers when you process in air. You must have in mind that the native oxide or the natural oxidation layer of niobium is of the order of 6 nanometers. So we are not affecting too much when we are processing the samples in nitrogen or in argon. Okay. This has been also confined by XPS spectra, in which you see that in all your case you observe the niobium-2 oxygen 5 oxide, that is the native oxide of the sample. And in the case of the sample that were processing in nitrogen, also you can observe a peak associated with the nitrogen, as I told you before. So this change on the surface can affect the superconducting properties. So first, we check it. We were measuring the evolution in the bulk superconductivity. First, we examine if there is some change in AC2. You can see that in the sample that were processed with the femtosecond laser, we don't see any change for all the samples we have analyzed, and only in the sample that was processed with the picosecond laser in nitrogen, we observe a small shift of 0.02 Tesla. But they are very similar in all the cases. So the laser treatment doesn't deteriorate AC2. When we measure the properties, the hysteresis loops, for instance, in this case, I show you what happened in 1 millimeter thick sample, and we observe that we have a small decrease at low field, but when we go to high fields, the sample that has been processed with laser is better. But we are just modifying the surface. So we were thinking, okay, if we are modifying the surface, both surface, because usually we treat both surface, and the sample is 1 millimeter thick, and we are measuring bulk superconductivity, we don't expect too much change due to the change on the surface, because we pin or we modify the pinning only in the two borders of the line. So then we repeat the same experiments, just working with a 20 microns thick sample, in which we expect more effect on if we modify the surface, also in the bulk superconductivity, and clearly you can see that we can modify the critical current density even at low field. In that case, it was processed. The best result we were obtained with a sample that were processed with the femtosecond laser, in which the effect on the surface was higher. So it seems that we can improve pinning properties even in bulk properties, and then we move to the surface superconductivity. In this case, the difference is that we apply the magnetic field parallel to the surface of the superconductor. Also, here you can observe that after laser processing, the behavior of this, we are able to decrease the we are able to decrease the critical current when we are above AC2. So we are modifying what will happen between AC2 and AC3, reducing the values of the currents above AC2. That is good for microwave applications. Okay. Here you also can measure the same behavior, just applying a DC field and measuring the AC susceptibility. You start with high fields and then you decrease the field, and you see, for instance, how the absorption of the sample that was not processed in air starts at high fields, while the sample that has been processed with laser, this has been shifted to lower fields and is sharper. So here is just a review of results we have obtained, and clearly you can see that AC3 is reduced strongly to near 60% of the value when you process in air. With laser. And it's not so big difference when you are using 1 atmosphere or others. Okay. Also, if you do with the picosecond UV laser, you also observe the shift of the transition from the non-irradiated sample to the irradiated ones. And one thing, the main difference between this sample and what I have shown you before is that this sample doesn't show anisotropy. In the other sample, clearly, you see a small anisotropy. So this is different, and you see the AC3 is different. You apply the magnetic field parallel or perpendicular to the nanostructure. In the case of this sample that we're processing with the 300 picosecond UV laser, the nanostructure is completely different, and you reduce this anisotropy. Okay, so as conclusion, I think that I have shown you that laser irradiation clearly affects the surface superconductivity properties, reducing Ag33 values. Generally, the anisotropy you can generate with the laser also is reflected in the superconducting properties. We have observed that when we change the atmosphere, we change a little the degree of the oxidation on the surface, but we do not modify the superconducting property. So I think that I can convince you that laser processing is an alternative to well-established technology to control the niobium superconducting, the surface superconductivity properties of niobium. Thank you very much.
I was wondering if you have done this type of study with higher temperature superconductors, not necessarily copper, because I assume that would be impossible, but for instance in iron pnictides or any other layer superconductor?
No, yeah. No, yeah, we have started with just with niobium. Okay, we want to move now to niobium nitride or niobium titanium alloys, but now we have started with niobium.
Okay, thank you very much.
Did you try to apply your technology to the high temperature superconductor?
I mean, the idea is that you modify the surface, the external surface, so in high temperature superconductors, you have the metallic coating layers, the silver or the copper outside.
You may take a film.
Yeah, it's possible, but we have not done yet. But it's possible. Okay. So,
any question online? Okay, last question, please.
Okay. Thank you, Liz, for the very conclusive presentation. And you talk about anisotropy, and when you talk about anisotropy and you do some surface treatment, is it due to the just surface morphology?
No, it's due because the structures you obtain with the laser are perpendicular to the polarization of the laser. You have a linear polarization on your laser, all the nanostructure is perpendicular to it. So at the end, your so you have this kind of, so this is induced by the laser, not by the previous anisotropy you have on your sample.
What was the reason for choosing niobium?
Because, I mean, these structures are very nice observed in metals. Also, it has been observed in some oxides, so that's why also we are thinking in maybe in the high temperature superconductor later. But the initial idea was, okay, because it's easier to obtain niobium, to buy niobium and to be superconductor, and it's metallic. It was the...
Okay, thank you.
Just, I wanted just to finish with this, okay, because Professor Navarro passed away 1 year ago, just while we were making this report. Okay, thank you.